Okay, so we're going to pick up with talking about areas between curves. So let me go into writing mode. There we go. Awesome. Okay, so let's move over to here. Okay, so let's just quickly review what we went over last time. So we have now two curves, an F and a G, and we want to find the area between them. And we found out that it's pretty easy to do this. You're going to integrate from a to b f of x minus g of x, right? Because that gives you the height of the rectangle that you're interested in. This should look familiar from yesterday. And we did a quick example where it's like we had two lines. You know, we wanted to estimate that trapezoid area right there. So it's pretty straightforward. You just integrated from 2 to 4, f of x minus g of x. And we moved on to a slightly more complicated example where like one of them is curved. So we wanted the area under the parabola but above the green line. Again, pretty straightforward. But I think I pointed out that oftentimes they won't give you the limits of integration. You'll have to set your two functions equal to each other and solve to find the points of intersection, right? So if you look at that parabola and the green line, when you solve, you find out that they intersect at -2 and +6. So you have to end up integrating from -2 to +6. So just be aware that you have to figure this out for yourself sometimes. And then it was pretty straightforward. We did the integration from -2 to +6. We did f of x, the top function minus the bottom function. Okay. Let's scroll a little. Go down. Now, you have to be careful if the top curve changes. Oops. Let me change this. Ooh, okay, wait. I'm adjusting my window. There we go, that's a little better. Okay, let's put the writing underneath my face. There we go. You have to be careful if the top curve changes. So here we have two curves. We have our blue curve, which is f of x. We have our green curve, which is g of x. You can see, so we're starting at x equals a and we're going to x equals b. And you can see that you get two different regions. So for the first region on the left, which I call region 1, you can see that f of x is the top curve. But then they intersect, and in region 2, f of x is on the bottom of the curve. So you have to be extra careful when you're dealing with cases like this. And the way you're going to do that is you're going to integrate from a to b the absolute value of f of x minus g of x. And what ends up happening is that you're going to split your problem into two different integrals. So for this example that we did right here, you have the area between cosine and sine. And you can see because sine and cosine are periodic, they switch, right? So for the first region, cosine is on top, but then for the second region, cosine is on bottom. And they intersect at pi over 4. So what ends up happening is you have to split your single integral into two different integrals. So you can see where it says the green number 1. We first integrate from 0 to pi over 4. Because from 0 to pi over 4, it remains constant about which one is on top, right? Cosine is on top there. But then from pi over 4 to 4, it switches, right? So you split your integral up into the different parts. So you figure out, oh, here's one part, and then this one's on top and this one's on top, but then in the next part, they switch. So you have to break up another integral for that. And if they were to switch again, you'd have to do another integral. Okay, we went through and we calculated this yesterday. So hopefully this sort of reminds you of what we were doing. Before I go forward, are there any questions you have about this concept of breaking it up when which functions on top changes? Just give a moment to think about it. Hopefully you're doing well. Okay, cool. If you think of something, just ask. I just want to give you a moment to so you can pause and think a little. Look over your notes from yesterday. Okay, so we're going to pick up here then. And what we're going to talk about is, what about if what if your area is defined with respect to the y variable and not x? What if your area, or let's say the area, what if the area is defined with respect to y and not x? So let me explain, what do I mean by that? So let me draw a little x and y axis. So here's your, well, what's that? Okay, here's your x-axis, here's your y-axis. Okay, let's draw our function f of x. Okay, let's have our other function g of x. So here's x equals a, here's x equals b. Now let's say we're interested in this area. Okay, this area is defined with respect to x because we want the area under f of x above g of x and between x equals a and x equals b. Alright, so notice the between x equals a and x equals b, it's defined with respect to x. That's those vertical lines, right? That will tell you what you integrate between. Okay, so that's what I mean by defined with respect to x. What we're going to be interested in now is, what if you define it with respect to y? So I'm going to draw in another axis. Let's put it, okay, well, that was not what I wanted. Okay, so here's our x and y axis. Okay, and let's say that one of your functions looks like this. How should I draw it? Let's draw it like this. This is f of y. I'm now using y as my independent variable. And over here, I have g of y. Okay, now, because y is the independent variable, really, when you're looking at this, you should be turning. Does that make sense? Y is now what your x-axis should be. Does that make sense? Like normally x-axis is horizontal. So when you think about this, like imagine turning your head and the y-axis is your horizontal. Can everyone see me in the camera like I'm doing the tilting? Okay, that's how you need to be thinking about this. Which means when we talk about our bounds, we're going to be integrating from y equals a to y equals b. And this is now an area defined by y. And we are interested in this stuff. Okay, so when we're talking about regions defined by y, this is what we're talking about. Y is the independent variable. Your bounds are going to be determined by Y values. Okay, making sense so far? Okay. So, if you wanted to estimate this area here, you would do a sigma of I equals 1 to n, and you'd have a rectangle. So I'm going to like draw in a rectangle. So notice now that my rectangles look horizontal, right? So remember how before you had a rectangle would look like this? So how wide was this rectangle on the left? It would be delta x, right? And then the height of this rectangle was f of x minus g of x. Okay, so the y case is going to be pretty similar, except for now, what is the quote-unquote width of this rectangle on the right? Remember, you're looking at it sideways? So what's the width of the rectangle on the y side going to be called? Delta y, exactly. So this is going to be delta y, and it's the same formula. It's going to be b minus a over n, right? Now, what's the height of this rectangle going to be determined by? Which one is the top curve if you have your head tilted? So what do we think? Yes, the top is f of y. So your height is now f of y minus g of y. Okay. So what you're going to get is f of yi minus g of yi times delta y. Okay. Now, if you actually want to, if you don't want to estimate the area, but you want the actual area, what do you need to do to this sigma, this Riemann sum? So this would be an approximation because you're just adding together n rectangles. How do you actually find the area? Like, what do you have to do to that Riemann sum? Yeah, you take the limit as n goes to infinity. So you're like, okay, let's just make the number of rectangles go to infinity. And then that is now a definite integral. This is the definite integral from a to b of f of y minus g of y dy. So luckily it all still works the same. But now your independent variable is y. So you just have to be aware of that. Okay, so I'm going to show you like how do you do this. So let's actually do this. Okay, did not let me type. So example, calculate the area of the region below defined by y. Okay, so I'm going to insert a beautiful x and y axis. Okay, and I'm going to have a parabola. So this is going to be f of x equals x squared. And I'm also going to have a line 2 minus x. Okay, I wanted that to be green. Excellent. So this is now g of x equals 2 minus x. And I want this region right here in red. R for region. Okay, you could solve this with respect to x, but we're going to solve it with respect to y. Okay, so what you need to do is you need to translate everything in terms of y. So the first step is to switch to the appropriate variables. Okay, so when it's in terms of x, you have an equation like y equals x squared. What would it mean? What would it mean for it to be in terms of y? Which variable would be solved for? So like f of x equals x squared and y equals x squared is the same thing, right? So what do I need to do to this equation to get it in terms of y? Right. But you will have to do that as like actual, yeah, solve for x. There we go. So I take the square root of both sides. Technically, the square root of x squared is absolute value x. But since the x's are all positive here, you can really just say that x equals root y. So really, the equation I'm dealing with is f of y equals root y. That's how I want to think of this. Does that sort of make sense? Like, if to do it for a y-defined region, you need a function in terms of y. Right? So you take your y equals x squared, you solve for x, and now you have a function in terms of y. F of y equals root y and f of x equals x squared give you the same graph. One in terms of x, one in terms of y. Okay, now you got to do the same thing for the other function. Y equals 2 minus x. So you solve for x, add x to both sides, subtract y from both sides, and apparently now we get that f of y equals 2 minus y. So that's how we want to think of the line. Not as g of x equals 2 minus x, but as, g of y equals 2 minus y. Okay, so is everyone on board with changing the variables? Anything we want to ask about that so far? Does it make sense why we're doing this? Because it was asked for the region defined by y, so we can't use x as our independent variable. Cool. Okay, now we need to figure out the limits of integration. We need to figure out what are the y values that these go between. So obviously, what y value does everything start at? Y equals 0, right? And then it ends at whatever this point of intersection is, right? So we need to solve for that. So I need to know when is f of y equal to g of y. So 2 will solve for the intersection to find the limits. So f of y is root y. g of y is 2 minus y. I'll square both sides. Y equals 4 minus 4y plus y squared. 0 equals y squared minus 5y plus 4. That factors into y minus 4, y minus 1. My solutions are 4 and 1. Did I do that right? Let's make sure I didn't screw up any arithmetic. Squaring 2 minus y is 4 minus 4y plus y squared. Subtracted the y, so you got minus 5y. Negative 4 times negative 1 is positive 4. Yeah, I did that right, yeah? For some reason, I just don't trust my arithmetic today. I just can feel it, like I'm gonna screw up. So, looking at this, which is the actual solution that we're interested in? Where do they actually intersect? Yeah, y equals 1. Cool. So now we can set up our integral that we need to solve. The integral that we need to solve is 0 to 1. And then you do the top curve. So which one is the top curve? If you turn your head sideways, which one is on top? You have G and you have F. Yeah, it's G. So remember, you turn sideways and you're like, oh yeah, you start at the y-axis, you go up, first you hit the blue curve, then you hit the green curve. So we're going to have G of y minus F of y. But notice, if once you go past y equals 1, do you see how the roles change? Like over here. Right? Do you see how the order is different depending upon y equals 0 to 1 or y equals 1 to infinity? Right? Do you see how the roles change? Right? After you go past y equals 1, the blue one is on top, which is why you got to be careful when you do this. Okay, and you get dy. So now we work on our integration. 0, 1. Okay, g of y is 2 minus y minus f of y is root y. So you get integral 0, 1. Okay, so let's find the antiderivative here. Okay, antiderivative of 2 is 2y. Antiderivative of minus y is 1/2 y squared. Root y is y to the 1/2. Antiderivative of that is y to the 3/2 times 2/3. So actually I don't need the integral sign again. We can just calculate what the answer is. So we're going to plug 1 into the antiderivative, plug 0 into the antiderivative, and find out what that is. Let's plug 1 in first. So you're going to get 2 times 1 minus 1/2 times 1 squared minus 2/3 1 to the 3/2 minus, and then you plug 0 in, you get 2 times 0 minus 1/2 0 squared minus 2/3 0 to the 3/2. And thank God there's the zeros there because they just go away. You're like, yes! That's a lot easier. Okay, now you gotta do some arithmetic. We're gonna get 4 minus 1/2. 1 to the 2/3 is just 1, so that's minus 2/3. Oh, crap. Okay, so let's do everything in terms of thirds. 2 2 times 1 equals 4. Oh! Oh shit, I see. Thank you. That was a good catch. I saw you wrote that in there and I was like, well, what the hell? What is this bullshit? And then I'm like, oh, I see. It's my bullshit. That was a good catch. Okay. Yeah, 2 times 1 is not 4. Wow. Okay. So all of it in thirds. 2 times 3 is 6. 6 thirds. Actually, they can't be thirds. It needs to be sixths. That's going to be 12 sixths times 3 sixths minus 4 sixths. See, I told you, remember earlier I was like, I don't think I can do arithmetic today? I wasn't joking around. 12 minus 3 is 9, 9 minus 4 is 5, and you get 5 sixths. Boom. That is the area of the region. We did it by having the region defined by y. Okay. And actually, does everyone agree that we could have solved this problem by defining it in terms of x? Right? But there's something really important that you would have had to have done. And we're going to zoom in to look at that. Why would you not want to do this in terms of x? I'm going to give you a moment to look at it. Why was it a good choice to do it in terms of y and not x? I'm going to draw a little line to sort of show you why. I'm going to draw like a little rectangle right here and a little rectangle right here. We would have to solve 2 areas. Because the first rectangle on the left, you see how blue is on top? But on the rectangle on the right, what determines its height? Green. So you would have had to have split the integral into 2 different problems. Whereas with y, it was pretty straightforward. If you look at it sideways, green is always on top, blue is always on bottom. That was just one integral to solve. Okay, so usually... Isn't this so cool? I could just zoom in. Like, I thought that was so nice. Imagine if it was like a board. I'd have to be like, everyone come up here and look. So let's just sort of write some notes here. Like, why would you want to define your region by y? Why would you want to define your region in terms of y? Well, perhaps if you define the region in terms of y, you might only have to solve one integral instead of 2. Okay, so hopefully what I'm saying makes sense, and that right, the picture I had above. Oops, whoa, what did I do? Okay, that was weird. Okay, so hopefully that's making sense. Like, why would you want to do this? Because it just might make it easier. If you look at it in terms of y, maybe one function's always on top and one's on bottom. But if you were to switch it and look at x, maybe one function will be on top for this part, and then another function will be on top for the other part. Okay, so that just makes your life easier. Wow. Okay. Yay! We're done with Chapter 2, Section 1. Woo! We're trucking along. Okay, so now we're going to start a new topic. And we've got, how much time to do this? We end at like 12:15, right? Or 12:10? Okay, we have like half an hour, cool. So let's keep going. So let me add a page. This is going to be about determining volume by slicing. zoom. There we go. Okay. So this is gonna be fun. Because I'm gonna have to like draw stuff. Okay, I'm like psyching myself up to do this. Because I'm like, oh my god, it's gonna be hard. Well, it's not that bad, but like, I gotta be in the right mood. Okay, this is the floor of my object. So I'm like, it's like gonna be like a weird, like, trapezoidal looking thing. Okay, so I'm gonna use like different colors so that you can like sort of... So does everyone see how it's like a box that we sort of like smash down this end over here and also smash down that end over there? Like we started with a box and then you crushed it on one side. So you see how it's like sloping down? Hopefully that comes across. Okay, so this is a three-dimensional region. It has volume. Okay, and I want to type that and it's like not letting me. There we go. This is a three-dimensional region. We were dealing with two-dimensional regions before. Okay, which has volume. Previously, we worked with two-dimensional regions, which had area. Oh, three-dimensional. So the question now becomes, how do you get this volume? Like, how do you figure that out? If you can use integrals to calculate areas, then maybe somehow you can use integrals to calculate volumes. Okay. So what we're interested in looking at is a cross-section of this. So hopefully these dashed lines show you how this is working. Okay, so do you see how I put like a sheet of paper so that it's cutting through and it would touch right here? Remember how I told you like this is going to be a lot of drawing? I'm actually doing pretty well, I think. So this sheet of paper intersects with my shape. Right? You can imagine I had this sheet of paper, it's like I sliced the box and you can see right where it cuts it. This is called a cross-section. A cross-section is what you get when you have a three-dimensional shape and you slice it with a two-dimensional shape, right? Does it make sense? A plane is two-dimensional, so it's like you made a cut through it. So what's a cross-section? It's the intersection of a 3D shape with a plane, which is a 2D shape. Okay, that cross section right there, it only has area. Does that make sense? That little stuff in white. Now, as you move the cross section, something interesting happens. Let's make another cross section in red. Okay, so does everyone see how I like moved my sheet of paper like back basically? And it intersects over here. I'm like trying so hard not to make this like fall apart. You know they like invented computers to do all this like 3D rendering and stuff. I'm like I guess if I had like a thing to do that for me, it would probably look nicer. But hopefully everyone's sort of seeing it. Do we see the other cross section? It's like, or if I just like made everyone feel like, oh my god, what the hell are these like rambling drawings that this man has made? Okay, cool. Because our box was like crushed on one end, what can you say about the cross section of the red one versus the cross section of the white one? Thank you. Yes. This one has more area. Okay. Now, this is going to be really cool. What we're going to do is, remember how to estimate area, you would take little rectangles and add them together? Okay, what we're going to do now is, instead of dealing with rectangles, we're going to deal with, let me draw them better. What should I call this shape? Rectangular prism? Yeah, that is actually technically what it is. So instead of adding together rectangles, we're going to add together rectangular prisms, because these rectangular prisms have areas. So you're going to think of this box as something that looks like this. Here's a rectangular prism. Oops, I made like an Escher drawing accidentally. Yeah, it's a 3D rectangle. And then my next rectangular prism, it's not going to be quite as wide. And my next rectangular prism is going to be not quite as wide. Is everyone seeing how it's like going, it's narrowing in on its width and its height, just like the thing that I had above? Can we see like this green line right here? That's right there. And this green line right here, that's going like that. So do we sort of see how like those boxes stacked together look a lot like this object, right? Do you see how they're tapering in on the width and they're tapering down on the height? Okay, so the area is equal to the sum of some individual smaller areas. Oh, actually, wait, let me back up. It's going to be the sum of something. We're going to talk about what the something is. Okay, so, oops. This area is the cross section, or so this cross section has an area, yes? I'm going to call that AXI. Cool. That cross section has an area. How can you make that cross section into a rectangular prism you can just extend it out a little. Does it make sense? That cross section, I can make it a rectangular prism by like fattening it out. I start off with a sheet of paper and then we're just going to stretch it out. So we're going to stretch it out by an amount delta x. So we're starting off with a sheet of paper, and that sheet of paper has some area xi, and then we're going to add some oomph to it. The oomph that we're adding is with delta x. So we're saying this side has area AXI. So what's the volume of this thing equal to? It has area AXI. How do you get the volume of the whole thing? Oh shit. You did see what I was drawing the whole time. It was behind my face. I apologize. No wonder everyone's just looking. Okay, I need to move it. I realized what I was drawing was behind my face. Let me move it. Okay, or I'll just redraw it. My bad. I can see why now people are like, what the hell is he talking about? Like, does it make sense I was like drawing on a part of the screen where you couldn't see? I feel bad now. Okay. Let's start off with a sheet of paper. There we go. Here's your sheet of paper. It's like that cross section, the white cross section. Yeah, so this sheet of paper has area AXI. And we're going to turn this into a rectangular prism by extending it. And we're going to extend it out by the width delta x. So does it make sense? The volume of this thing is the area of the white part times the width delta x. Does that idea make sense to people? Like, you take your sheet of paper and you stretch it out and now you have a rectangular prism. Yes? No? How do we feel about that? I need reacts. Okay, cool. Now, what you're going to do is you're going to add together a bunch of these rectangular prisms. So you're going to have sigma AXI delta x. That's just what's going on right here, right? You remember how I did a bunch of these little rectangular prisms? You add the area of those rectangular prisms and boom, you've now estimated my original box area. I don't know what the heck to call it. Now here's the cool thing. What does this look a lot like? What does it remind you of? This formula. Yeah, let's get some infinite prisms going. Exactly. It looks like a Riemann sum. How did you turn a Riemann sum into... Yeah, it looks like a Riemann sum. How did we turn a Riemann sum into a definite integral? You took the limit of it. So you look at this and you're like, holy shit. Okay, what I'm going to do is to... Actually, I should put volume here. This is a volume. To calculate my volume, I'm going to take the limit as n goes to infinity of my sum of my rectangular prisms. Which means this is just some integral from a to b of some area function dx. And this area function is the area of a cross section. So if you can figure out a formula for the area of a cross section, if you integrate that, you get the volume. So let's actually show you how this will work. It's actually pretty cool. Okay, so we call this the slice method. So this is the slice or cross-section method. The slice is another word for cross-section. Method for determining volume. Basically, first you should figure out your cross section. Usually that involves drawing a picture. 2, figure out a formula for the area of the cross section, or slice, whatever you want to call it. 3, finally, integrate said formula to find the volume. Yeah, integrate the area, then you integrate once. You integrate the area to get the volume. One integration. Yeah, it's basically exactly what we did before, but now we're dealing with three-dimensional objects, which, like what I was saying at the beginning, remember I was like, I really need to psych myself up to draw this properly. It's actually a pretty decent drawing, to be honest. I remember when I learned this, my professor was like really shitty at drawing it. And I remember just looking at the picture and thinking like, oh my god, like I have no idea what he's talking about. So hopefully that's not your experience. Okay, so let's do this with an example. So what we're gonna do is we're gonna example. We're going to use the slice method to calculate the volume of a pyramid. Is that how you spell pyramid? I think so. Looks good enough. It's a weird word. Okay, and I'm gonna try really hard to like make sure that this drawing makes sense. Okay, here we go. This is gonna be the x-axis. And this is gonna be the y-axis. So we don't really care, but does it make sense that the z-axis is like that? Cool. Okay. Here's our origin. Drawing this pyramid is gonna look weird. I'm just like telling you now. I'm gonna try. Okay, so you can imagine the pyramid starts at that point at the origin and goes up and oops, okay, I went too vigorously. Goes up and out. And let's say it ends right here. So I'm going to draw the little... So does everyone see the cross section? It's centered around the x-axis. So you can see the little dots. Like the pyramid, its bottom is this flat sheet of paper, which means the other edges need to look like this. Okay, so I'm going to draw in some lines. Do you see how that's one triangular face right there? And then here is a other triangular face right here. Wow, it's actually not that bad. I could do like a way worse job. Okay, then I'm not going to draw in the other triangular faces. Does that sound cool? Because it's just going to look weird. Does it make sense? I'm going to just draw like one line for it. There's other triangular face over here, and then other triangular face over here. Right? They go like that. Cool. Okay, so let's do this. So this is the 3D view. We actually really only care about the 2D view. So we can draw our x-axis like this. Okay. And we can draw our y-axis like this. And what you've got going on is a line going up like that, a line going down like that, and this, oops, it's a little broke back. Let's make that straighter. Okay, right here was the base. And right, you can see that the base is that thing. But in the 3D view, you see it as a cross section. On the 2D view, you just see it as a line, right? Because it's the line and you're not seeing how it's like this. Okay? So that makes sense, the equivalence of these two things. So all your little cross sections would be like this. So a cross section would be over here. Do we see how those two white things are equivalent? I just need to know if that makes sense or no. I'm gonna let you think for a moment. Okay, what shape do I have for my cross section? Actually, it's not necessarily a square. Yeah, it's a rectangle. And let's talk about why it's a rectangle and not necessarily a square. So let's say that here's like a line. So this would be like y equals ax. Yeah. Okay, so if the slope is ax for that one, what's the slope of this one gonna be? So yeah, let's think about it. If the slope is ax, what's this point literally right here? Or let's come up with a point here. Let's say that this is what should we call this x value? So let's say that, how far are we going to go out? Normally when you're dealing with a pyramid, what do you need to know about the pyramid? Yeah, cool. So this will be x value h, which means how tall is the y value there? AH, right? So this is AH. So we also want this one to be, well, that's going to be negative AH. So this point right here is H. So yeah, it's going to be y equals negative AX. Yeah. Uh-huh, yes. If it's a rectangle, say that again. Wait. Say that again. Yeah. So you have these sides like this, and then you have those sides like this, right? The area. Well, you don't have area for sides. You have the area for the whole rectangle. So I'm not quite sure what you're saying there. Oh, oh my god. Did we run out of time too? Okay, so we're gonna pick this up next time. We have it set up. We're like almost there, but I want to like draw out all the steps so you can see what's happening because these are actually pretty difficult to do. Okay, so we're gonna stop right here. This is one of the harder things we're doing.